Greetings. These are the Homework 1.5 solutions for AP Physics 1. So, number 23 from the Giancoli text says, a car accelerates from 14 meters per second to 21 meters per second in 6 seconds. So, in order to kind of build our problem-solving technique, we're going to go ahead and start writing out our givens and our knowns and our unknowns. So I have from 14 meters per second, so that's V initial of 14 meters per second, to 21 meters per second, so that's my V final, in 6 seconds, so my time is 6 seconds. And now I really can say this is t or this is delta t, more specifically. So I want to calculate its acceleration. So my acceleration average is V minus V initial over delta t. So substituting our values, we have 21 minus 14 over 6. And that's meters per second on top and seconds in the denominator. So my average acceleration ends up being 7/6 or we'll go ahead and round this to 1.17 meters per second squared. Now you could round that to 1.2 as well. That may be what the textbook offers. So the second question is, how far did it travel in this time? So now I want to use my initial final velocities, my acceleration, and I want to look for, so this is the second part of the question, delta x. I want to know how far it moved or how far it changed positions. So I have velocity, initial and final, and acceleration, and I'm looking for delta x. So this tells me I want to use the equation where I have v squared, v initial squared, plus 2a delta x. Alternatively, you can use time. You could just as easily use the second kinematic equation, which is delta x equals v naught t plus 1/2 a t squared. However, I don't like dealing with the t squareds, but I guess you could. So I will go in and I will solve, actually, you know what? I think I am going to use this one now that I think about it, because it's already solved for delta x. I don't have to do any rearranging. So given this, we now have delta x is equal to my initial speed of 14 times 6 seconds plus 1/2 times my acceleration that I just found, which is 1.17, times my 6 seconds squared. I didn't need to include the seconds there, but I think it's sometimes a habit to include it. So take this into the calculator, and we get approximately 105 meters. So there we go. So keep in mind, you could use really either of these equations. I just used this one because it was easier since I didn't need to rearrange. For the next question, question 25, we have a pitcher throwing a baseball with a speed of 43 meters per second. So that's his throwing speed, and we kind of see that shown in our little diagram here, where he starts with the ball here, and then he throws it, and when it leaves his hand, it's at 43 meters per second. So my initial velocity is going to be 0, because I'm just holding the ball to begin with. My final velocity will be 43, because that's what it's leaving his hand at. Now, in throwing it, it says the pitcher accelerates it through a displacement of about 3.5 meters. So my displacement is 3.5 meters. Very simple to get that. So I want to estimate the average acceleration of the ball. So I'm looking for acceleration in this case. So I have v naught, v, delta x, and a. So here, I definitely want to use the equation v squared equals v naught squared plus 2a delta x, because that includes all of these different variables that I pulled out of the problem. So the first thing I'm going to do is rearrange this to solve for a. I'm going to isolate the a in this equation. So I'm going to subtract v naught squared. So I have 2a delta x, and then I'm going to divide both sides by 2 delta x, and I'm going to move a to the other side, just because I like the thing I've solved for to be on the left. Sorry about that. Over 2 times delta x. So now I'm going to go ahead and substitute my values. So for my acceleration, I'm going to have 43 squared minus 0 squared, which is 0, over 2 times 3.5 HW1.5. So my acceleration when I plug this into my calculator is a whopping 264 meters per second squared. And I know that because this is meters per second, and I'm squaring it over meters. So if I look at the units, I have meters squared over seconds squared over meters. So one of my meters will cancel and leave me just meters per second squared. So that's how I know that I put my numbers in the right spot. And that's my acceleration. For question 27, it says a car slows down uniformly. So uniformly is just a fancy word for saying constant acceleration from a speed of 28 meters per second to rest. So that means my initial speed is 28 meters per second, and my final speed is 0, right? That's rest, in 8 seconds. So the time that elapses is 8 seconds. How far did it travel? So I'm looking for delta x. So I have v naught, v, t, and delta x. So you may notice that this is not actually going to come straight from one of my equations. It's actually going to come from the definition of average velocity. So I know that average velocity can be found 2 different ways. I guess I don't need the bar and the subscript. So my 2 different ways are, I can say final plus initial velocity divided by 2. I can also say displacement divided by time. These are both valid ways to say average velocity. So this equation here includes all 4 things that I was given. So I can say my average velocity is 0 plus 28 over 2, and that's going to be equal to my delta x divided by 8. So I now have 28 divided by 2, which is 14, times 8 is my delta x. And so how far did I actually move? I moved 112 meters. So keep in mind that even though this is not a kinematic equation, I do need to have both of these definitions for the average velocity. So for question 33, we have a 75-meter long train that you can see in the diagram, and it begins to again uniformly accelerate, so constant acceleration from rest. So I know that my initial velocity, v naught, is 0. I started from rest. The front of the train has a speed of 18 meters per second when it passes a railway worker who's standing 180 meters from where the train started. So delta x in this case is 180 meters. So don't let this 75-meter thing confuse you right now. So I want to first start by figuring out what this acceleration is. So I have v naught, I have v final, I have delta x. That tells me I can use my third kinematic equation to figure out acceleration. So the third is the v squared equals v naught squared plus 2a delta x. And again, I'm solving for acceleration. So if you want to see that solved, go back to the earlier problem we did that in. And I have v squared minus v naught squared over 2 delta x. I'll just go ahead and substitute in here. So I have my v final, which is 18. Don't forget to square, over, minus 0 squared, all over 2 times 180. So the acceleration of my car ends up being only 0.9 meters per second squared. Now, the actual question says, what will the speed of the last car be as it passes the worker? So really what's happening is this is for the front of the car to get to the worker. Now I want to know, what is this final speed when this distance has traveled or been traveled by the car? So this is my second distance, so it's moved 75 more meters. I can even say this is delta x1. So I want to go in and say, all right, now how much faster is it going to be after it's traveled 75 more meters? So I'm going to go ahead and use the exact same equation because acceleration is the same. So acceleration is still 0.9, except I'm going to use my initial velocity, which is 18, and my new final velocity, so it was 18 at this instant, and my final velocity now is unknown, and I've moved a distance of 75 meters. So this time I'm going to look for v final. So I've already solved for v final here. So I have v squared is going to be equal to 18 squared plus 2 times 0.9 times my now displacement of 75 meters. And that's going to give me 459 that I'm going to square root here. And so my final velocity should end up being 21.4 meters per second after the car has gone, or the train cars have gone past this worker. So question number 37, if you pay attention, has a Roman numeral 3 next to it, which means this is the hardest of the hard questions that can come out of the textbook. So if you can do this question, or you know how to do it, you're doing extremely well. But this should be considered kind of the upper limit of difficulty. So we have Mary and Sally who are racing. When Mary is 22 meters from the finish line, she has a speed of 4 meters per second. And Sally is 5 meters ahead of her, who has a speed of 5 meters per second. So Sally thinks she has an easy race and slows down at a constant rate of 0.4 meters per second for the remainder of this race. So she has an acceleration of 0.4 meters per second squared. So I'll call this a Sally, and that's negative because it's going against her velocity. If Mary wants to finish at the same time and place as Sally, what does her acceleration need to be in order to do that? So I'm going to point out that Mary here is at the origin. This is our 0 mark. So Sally is at 5 meter mark. So Mary's initial position is 0, while Sally's is 5. Now we know that both of them have the same final position because they're both going to finish at the 22 meter mark. Now one other thing has to be true if they finish side by side. They must finish at the same time. So we just need to figure out when is Sally going to finish, and we can figure out what acceleration Mary needs to finish at the same time. So let's start by kind of writing out our knowns again. So I have for Sally, so I'm going to do Sally first. So Sally, so I have Sally, this is part 1. So Sally has a final position of 22 meters, an initial position of 5 meters. She has an initial velocity of 5 meters per second, and she has an acceleration of negative 0.4 meters per second squared. So if I want to know how long it takes her to get to the finish line, I'm just going to use the second kinematic equation, which is the x equals x naught plus v naught times t plus 1/2 a of Sally t squared. So plugging all of my numbers in, I have 22 is equal to 5 plus 5 times t plus 1/2 times negative 0.4 times t squared. So cleaning this up a little bit into something that I can solve, I need to actually set it up as a quadratic equation. So I'm going to have negative 17 plus 5t minus 0.2 t squared. Uh-oh, there's no easy way to factor this. So unfortunately, there's only 2 ways to do this. One of them is to either graph or use the quadratic equation to find when this is true, my solutions to this equation. So I'm going to go ahead and use the quadratic equation on my calculator, and I'm going to get 2 numbers out of this. I'm going to get 4.06 and 20.9. All right, So I have two numbers here. Now, the issue is I can't use both of these because really she can only finish at one time. Well, this right here is the 4-second mark. Essentially, Sally is 4 seconds ahead of Mary where they are right now. So I'm going to use the 20.9 second mark. So, you know what? I'm actually losing my mind. So really, what I should be saying is I'm using the 4.06 second mark. And that's because this is the first time that I reach 22 meters. Because if you think about it, Sally, if she continues to accelerate like this, is eventually going to start moving in the opposite direction. So I'm going to use this 4-second mark as the correct time for me to cross the finish line. So now that I know that, I can go into part 2. So part 2 is dealing with Mary. So Mary has a couple different things. She's still finishing at the 22-meter mark. Her initial position, however, is 0. Her initial speed is 4 meters per second, and her acceleration is unknown. But now I know that her time is 4.06 seconds. And honestly, we could probably round that to 4 if we wanted to, but we'll leave it as it is for now. So now I can go into my second equation, x equals x naught plus v naught t plus 1/2 the acceleration of Mary times t squared. And I can substitute all of these values in, and I'm solving for my acceleration in this case. So I have 22 is equal to 0 plus 4 times my time of also 4. I'll write 4.06 now. Plus 1/2 times my unknown acceleration times the 4.06 squared. So if I move this around, I would get that acceleration of Mary is going to be equal to an acceleration of essentially 0.7 meters per second per second. So there you have it. In order for Mary to cross at the exact same time, she needs to have an acceleration of 0.7 meters per second squared. So if you had difficulty with this, that is perfectly acceptable at this point. We are still in the early stages of working with kinematics, and this is a difficult problem. So if you got it, good job. If you didn't get it, still good job. You're getting there. Question 39 says, I have a stone dropped from the top of a cliff, and it's seen to hit the ground after 3.55 seconds. How tall is that cliff? So I'm going to sketch real quick. Here's my cliff. Here's a ball, or a stone rather, and I'm going to drop it, and it's going to hit the ground eventually. So initially, if I'm just dropping it, my speed is 0. I know that after 3.55 seconds, it hits the ground. I don't know how far it falls, so my change in y, my y displacement, is unknown. I do, however, know my acceleration. So my acceleration is, you can either say negative or positive 9.8. So actually, for sake of argument, let's say that the down direction is positive this time. That means my acceleration, which is down, is a positive 10 or 9.8 meters per second squared. Right? I'm going to write that's because down is positive this time. And that's just because it's convenient to say that. So now I have v naught, t, delta y, and a, and I want to know delta y. So if I go into my second kinematic equation, which is for y equals y naught plus v naught times t plus 1/2 a t squared. If I just look at the left side, I know that y minus y naught is the same thing as delta y. So that would be equal to v naught times t plus 1/2 times a t squared. So now I can just substitute in my values. So v naught is 0. That's nice. Our time was 3.55. Doesn't matter because that's 0. Plus 1/2 times my 10 that I'm using times my 3.5 seconds. I need to stop putting the s. squared gives me a height of approximately 63 meters. Now, if you use 9.8, you're going to get something slightly different, and the book may say something slightly different. And that's okay, because in AP, you can use either 9.8 or 10 for the acceleration due to gravity. Question 41, now we're on to Roman numeral 2 difficulty, says a player catches a ball 3 4/10 a second after throwing it vertically upward. So let's sketch this really quick. So here is my ball. It goes up, it comes back down. And so the total time that elapses is 3.4 seconds. And I threw it vertically upward, so I know that I have some initial velocity, and I don't know what that velocity is. So I'm going to say initial velocity, unknown. I still know that because I threw it into the air that my acceleration is 10 meters per second squared. And so this time I'm actually going to say that positive is up. So we'll say positive y is in the up direction. So now my acceleration actually has to be down in order for everything to be consistent. So I'm going to use negative 10 meters per second squared as my acceleration. So now I have one more thing. The question is, if I catch it right here, what other information do I know? Well, if this is my y coordinate, where I start from is exactly where I end. So I can say that my y, my final position, is equal to my initial position. Or you can say that delta y is equal to 0. So kind of shortcutting from the last equation we wrote, I have from the second kinematic equation that delta y is equal to v naught times t plus 1/2 at squared. So since delta y is 0, I have the following. If I solve for v naught, then I have, actually, you know what? We'll plug in the 0 first. So I have v naught t plus 1/2 at squared. And I'm solving for v naught. So I'm going to subtract the 1/2 at squared. So I have negative 1/2 at squared. And then I'm going to divide by t. So the actual result is that one of my t's cancel out, and I just have negative 1/2 at. So v naught must be negative 1/2 times my negative 10 acceleration times my 3.4 seconds. So what initial speed did I throw it with? Approximately 17 meters per second. So that's the first part of this question. The second part is, well, what height did it reach? So there's two ways to think about this. One of those is if v naught is equal to 17 meters per second, my acceleration is negative 10 meters per second squared, and I know that I'm looking for delta y. What happens at the very top of my arc? Well, at the very top of my arc, I would say that v, my final velocity, is 0, right? And that's at the top of my trajectory or my path. So given all of these, I can use a different equation. So I can use the third equation for this. So that's v squared equals v naught squared plus 2a delta y. So I'm going to solve for delta y again. So that's v squared minus v naught squared over 2a. And I'm going to substitute. So my final velocity is 0 minus 17 squared over 2 times negative 10. So plugging all these in my calculator, I will get approximately 14.5 meters. So there you go. So for question number 43, we have a kangaroo that jumps straight up to a vertical height of 1.45 meters. So I'm going to sketch this real quick. So even though it's straight up, I'm going to do a little bit of a curve. And it goes up a distance of 1.4, actually, let's label this. So delta y is equal to 1.45 meters. And how long was it in the air before returning to Earth? So I'm looking for time in this question. I know that acceleration is negative 10 meters per second squared. So I'm saying up is positive in this case. So this is positive y. And the other bit of information I know is that v final at the top is, well, let's do it like this. So we'll say v at the top is 0. So here's a little bit of a tricky one, because what I'm going to do is I'm going to see, all right, how long does it take to go up to the top? And then I know that it's going to be the exact same amount of time to come back down. So let's write out what I just said. So zooming in here a little bit. So the time to reach the peak height is going to be the time to fall from the peak to the ground. So with that information, I know these 4 things. Now let's see how that helps me. So I can actually say that if I start at 0 and fall down this distance with this acceleration, I can figure out the time. So I'm saying instead of final velocity, I'm going to just say this is initial velocity, because it depends on if I'm going this way, so if I'm going here and up, or if I'm coming down. So both of those should be the same amount of time. So with that, I can actually use the second kinematic equation, which is delta y is equal to v naught t plus 1/2 a t squared. So delta y is actually going to be a negative, because I'm going down. So I'm going to write negative 1.45, and that's equal to 0 times t plus 1/2 negative 10 times t squared. So I end up with negative 1.45 is equal to negative 5t squared. So t is going to be equal to the square root of 0.29. And so that time is 0.54, we'll say. So 0.54 seconds. So this is to fall 1.45 meters. So the total time will be equal to 2 times this. Right? And this is because this is my up and down. So my total time in the end is going to be 1.08 seconds. So there we go. So for question number 45, we have an object that starts from rest. So I know that, let me change colors. So I know that v initial is 0, and it falls under the influence of gravity. So I know that my acceleration is, let's go ahead and just say negative 10 meters per second squared. And I want to draw graphs of its speed and the distance it has fallen as a function of time from t equals 0 to t equals 5. So let's go ahead and sketch our graphs, but let's sketch them in the order that we're used to doing it, which is where we have position on top. So this is my, actually let's say distance, how about that? So this is my distance over time. And then below that, I'm going to do speed. So t, I'm just going to say v here for my speed. So I want to draw graphs of its speed and the distance it's fallen. So if I'm doing speed, then I don't care about the fact that this is negative. I just care that it is 10 meters per second squared. So why is that important? So here is my A. Well, if I start from rest, I'm going to start here at 0, and then I'm actually going to increase my speed at this rate. So if you remember, one of our equations is v equals v naught plus at. Because this a right here actually represents our slope. So if our a is equal to 10, that means my graph of velocity, or in this case speed, is actually going to be the same equation. So it's going to have a slope of 10. So this right here is going to be a straight line, as straight as I could get it with this pad. And at the 5-second mark, I'm going to have 5 times 10, so 50 meters per second as my speed. And I can calculate that using this equation. So now I want to look at the distance that it's fallen as a function of time. So here, I'm going to say, all right, I'm going to start at 0. Remember, this is distance fallen. So I'm starting at 0, and then I'm going to a higher distance. Right? So d0 is 0, and I'm increasing from there. So how does this look? Well, this is the slope of my line. So if you remember from our work with the kinematic graphs, if my velocity is changing, that means my distance or my position has to be curved. So the slope of my graph actually starts at 0 and increases. So I'm going to sketch that shape. It looks something like this. And just figure out at my endpoint where I'm going to be after 5 seconds. So in order to do this, I'm going to use the second kinematic equation, right? My x equals x naught plus v naught. Actually, I can do this with y. Let's do it with y. That makes more sense since we're falling. Y equals y naught plus v naught t plus 1/2 at squared. So if my y naught is 0, then my distance that I fall after 5 seconds is going to be 0 plus 0 times 5 plus 1/2 10 times 5 squared. So the distance that I fall is actually going to be 125 meters. So that is going to be this position right up here. Distance in meters. So here are my two graphs, and really the only thing that's important is that I find those endpoints. I find where I am at some particular instant, and I can get very nice graphs just from doing that. For question number 49, we have a helicopter that is ascending, which means it's rising, with a speed of 5.4 meters per second vertically. So let's see, we have this is my helicopter that's ascending. And it says at a height of 105 meters above the Earth. So, all right, here's the Earth. Here's how high I am. At a height of 105 meters, a package is dropped. So actually, let's call this Y initial, 105 meters. And then a package is dropped from the helicopter. How much time does it take for the package to reach the ground? So I'm looking for time. I know that acceleration is going to be negative 10 meters per second squared for g. And I want to know what v naught is for the package. Well, if the package is in the helicopter and it drops it, then the package has to be going the same speed as the helicopter when it's let go. So if the helicopter is going 5.4 meters per second up, then the package must be going 5.4 meters per second up. So here are my 4 things, and I know that when this package crashes into the ground, my final position is going to be 0. So I have everything I need to use the second equation, which is y equals y naught plus v naught t plus 1/2 at squared. So let's plug in all of our numbers and see what we have. 0 equals 105 plus 5.4 t, and then I'm going to go ahead and say 1/2 times negative 10. So I have negative 5 t squared. So again, I have a quadratic equation. So I have 2 ways to do it. I'm going to solve essentially using my calculator. You can use the quadratic equation, you can use graphing, whatever you would like in order to find the answers to this. So pause for a second and we go do that. So we get 2 numbers. So we have negative 4.07 seconds and positive 5.15 seconds. So here, the negative is kind of a weird number because that seems like it happened before the package was actually let go. So I'm actually going to ignore this one because it was before the package was let go. And it appears that my package will hit the ground in 5.15 seconds. because that happens after I let go of the package. And that's all there is to that, just a simple solving the quadratic equation in this case. For question 51, so we have a garden hose that's shooting a stream of water upward, and it starts at an initial height of 1.8 meters. So I'm going to say this is y naught, which is 1.8 meters. When I turn off the nozzle, I hear the water hitting the ground next to me for another 2.5 seconds. What is the speed as it leaves the nozzle? So I'm actually, in this case, looking for an initial speed. I know that my acceleration is going to be negative 10 meters per second squared. So when I turn off the hose, there's like a drop of water. Let's imagine one drop of water that goes up and it comes down and it's the last drop of water to hit. And that's going to happen after 2.5 seconds. So it takes 2.5 seconds to go up and hit the ground. So my final position has to be 0 when I hit the ground. So given all of this, it looks exactly like I want to use the second kinematic equation again. Y equals y naught plus v naught times t plus 1/2 at squared. I have everything except v naught. So plugging in some numbers, plugging in some numbers, I have 0 equals 1.8 plus v naught times 2.5 plus 1/2 times negative 10 times 2.5, don't forget to square. So simplifying this, I end up with 0 equals 1.8 plus 2.5 v naught minus 31.25. 31. So at this point, I'm just solving an algebra equation. So my v naught will end up being, let's say, approximately 12 meters per second. And I'm rounding this one a little bit because all of my previous numbers that I was given only started with 2 digits. So I'm going to keep 2 digits for my answer. And so again, we're just using the second kinematic equation to be a very versatile equation that we can use for a lot of different purposes. For question number 71, we have a stone that we throw upward with a speed of 15.5 meters per second. So V initial is 15.5 meters per second from the edge of a cliff that is 75 meters high. So Y initial, it actually says Y initial is 0, and then it's saying Y final is negative 75. And that's fine. We're setting the initial point as right where the ball starts. How much later does it reach the bottom of the cliff? So I know that my acceleration, pen got stuck. My acceleration is negative 10 meters per second squared, and I'm looking for time in this case. So I have initial speed, I have final and initial velocities, and I have an acceleration. So I'm going to go ahead and use that second kinematic equation again. So I have y equals y naught plus v naught t plus 1/2 at squared. So I have y final is negative 75 equals 0 plus 15.5 t, and I'm going to go ahead and say minus 5 t squared. We're going to see 1/2 times a when it's equal to the acceleration of gravity quite a bit. So this gives us a quadratic equation, unfortunately. So rearranging it, I have 0 equals 75 plus 15.5t minus 5t squared. So again, we have to solve a quadratic equation. I know, it's terrible. But when you go and do that, you end up with 2 times. So those times are negative 2.62 and, sorry about that, 5.72. So again, we have this negative number. So that would have been like if I had started at the bottom of the cliff and thrown it up. So we're not going to use the negative time. We're going to choose the positive time. So this is the length of time that it takes for our rock to hit the bottom of the cliff. Now B says, what is its speed just before hitting? Well, now that we have the time, this is actually really easy. So my speed is going to come from my first kinematic equation. V equals V naught plus AT. So my acceleration is the same, and I know the time, and I know my initial speed. my velocity. So my final velocity is going to be 15.5 minus 10 times my 5.72 that I just found. So my final velocity ends up being negative 41.7 meters per second. For the last part of this question, it's asking what is the total distance that it travels. So this is a little bit of a trickier question. So we're going to start by finding this distance, how far it goes up. Because we know that at the top, the speed is going to be 0. So I'm going to start by using the third kinematic equation with the following information. V naught is 15.5 meters per second. V final is 0. My acceleration is negative 10. And I'm looking for that little change in height. So my equation then sets up as v squared is equal to v naught squared plus 2a delta y. And I'm going to solve for delta y. So just like we've done in previous homework problems, we have v squared minus v naught squared over 2a. Substitution here is going to give us 0 minus 15.5 squared, that is a 2, 15.5 squared over 2 times negative 10. And so that height that we go up is, we're going to round to 12 meters. So I have this 12 meter, I'm just going to circle it instead of box it because that means that this distance that we go up is 12 meters. Now we're asked for distance. So we go up 12 meters. So that's 12 meters. Let's write this over here. So we have 12 meters plus we come back down another 12 meters. Then we fall all the way to the bottom, which is a distance of 75 meters. So the total distance that we traveled here has to be 75 plus 24, which is 99 meters. Finally, our final question, number 78. So this shows two position versus time graphs for bicycles A and B. So A kind of curves and B is a straight line. A asks us to identify any instant at which the two bikes have the same velocity. So what does that mean? Same velocity means same slope. So if I take a look at this, B has the same slope all the time. So really I just need to identify the instant when A has the same slope. So that would be right here about when the tangent line to A is parallel to B. So my instant when they have the same velocity must be this instant right here. So I'm going to call this TA. Now changing colors, we're going to say, all right, B asks us which bicycle has the larger acceleration. Well, let's take a look. So the acceleration of bicycle B has to be 0, and that's because it's a straight line, right? The acceleration of A, however, has to have some kind of acceleration because it starts with a low slope and it goes to a higher slope. So all I know is that the acceleration of A has to be larger than 0 because it curves upward. Therefore, the bicycle with the larger acceleration has to be A. Now moving on to C. At which instant are the bicycles passing each other? So passing means they are at the same position. So there are actually 2 times when they have the same position, right here and right here. So at the first instant, B is passing A because its position goes ahead, and in the second instant, A is passing B. So we'll say that this position right here is TC1, And this one right here is TC2. Now for D, it asks which bicycle has the larger instantaneous velocity. So this means which one ends up having the largest slope at any point. So instantaneous velocity, so we're going to say V inst, means which one has the steepest slope at any point. So which one ends up having the steepest slope? Well, that is very obviously bicycle A, because at the very end of its motion, it has a very steep slope. And finally, which one has the larger average velocity? All right, this is kind of a tougher one, because remember, it's change in position over time. So if we go into this and we say, let's see, I got to figure out which color I want to use. So if we go into this and we say which one has the largest average velocity, so V average is change in position over change in time. Well, they both go the same time, and it looks like they end up about the same distance away from each other. So honestly, if you were to look at just this time interval, it appears that they have the same. At least for this time interval. So there you go. Just a bit of review using graphs and how these things come up in comparing motion.